All right, we're going to get started with our panel titled Updates on QEC Roadmaps. I will start by introducing our moderator for the panel session, which is Yuval Boger, Chief Commercial Officer from QuEra Computing. I will allow you to have the others introduce themselves.
Wonderful. Thank you very much, and thank you everyone that's here. So why don't we get started? Jeremy, who are you and what do you do?
Yeah, hi everybody. My name's Jeremy. I'm the technology development lead at Alice & Bob, and I'm a quantum physicist working on some of our biggest hardware problems at Alice & Bob.
And Michael?
Hi, my name's Mike. I'm just a simple research scientist at Google Quantum AI. I work mostly on quantum error correction.
There are no simple research scientists in quantum error correction.
You found the first one.
Jin-Sung?
I'm Jin-Sung Kim. I'm a developer relations manager for quantum computing at NVIDIA, so I manage a lot of our strategic partnerships. So I've been at NVIDIA for about 3 years. Used to be a research scientist at IBM.
And Przemyslaw?
Hi. So I am also quantum research scientist, but at AWS. So you might know AWS from different quantum directions we are exploring and contributing to the field. Probably you've heard about Bracket. I am from Center for Quantum Computing. We are building hardware based on superconducting qubits. Our center is based on the Caltech campus. And I am primarily working on quantum error correction theory and both closely with the experimentalists.
So once upon a time, someone told me that physicists only care about the derivative. They don't ask you, how are you? They ask you, what's new? So why don't I ask you all physicists, what's new in your work on QEC since, say, Q2B last year? And Mike, maybe we start with you.
Sure. So as you guys saw from Hartmut's nice talk this morning, the most recent thing we did was we demonstrated a below-threshold quantum memory. This is something we've been working on for, well, I would say the field's been working on for a few decades. So we're really excited about that. And then I think sort of where we're going to next is sort of looking at logical operations and just building the systems bigger and better.
And Jeremy, what's new on your side?
Yeah, so we've had a full year full of lots of physical results. So in the beginning of the year, we were talking about LDPC codes and how they reduced the number of qubits we were going to need to build a universal quantum computer. We've also had some results about novel types of qubits and how we can increase the hardware efficiency at the Hamiltonian level. And just last week, we released our public roadmap to useful quantum computing in 2030, which has been basically the concatenation of a lot of incremental works, trying to get together a roadmap which we think makes a lot of sense and is supported by the advantages which are brought by cat qubits.
Przemyslaw?
So at AWS, we really think long-term. So we have really huge effort on theory and QEC side. So there is a bunch of interesting papers on that side, but I wanted to highlight our work on experimental side. Here we are thinking about hardware efficient quantum error correction, similarly to Alice and Bob. We also investigate cat qubits as components of our codes, and we have very exciting results on, I would say, a milestone in the field where we showed how to really combine those cat qubits and build a memory which is better as we scale it up.
Jin-Sung?
So actually today, Inflection announced in collaboration with NVIDIA some of the first examples of a demonstration of a material science application using neutral atom logical qubits. So we're very happy to be a part of that work. This is run in Q2Q, which is our platform for doing hybrid quantum classical applications. It's scalable, it's flexible, it allows users to invoke GPUs and CPUs performantly alongside quantum processors. And we also have a new library that we released within Q2Q called Q2Q QEC. So what this has is several pre-built QEC codes, for example, Shor's code, the Steam code, as well as some pre-built decoders, and allows the user to also bring their own decoder, leverage the GPU for doing these types of GPU-accelerated decoding tasks. In addition to that, we've also had the first examples of results coming out of our DGX quantum system. So what this is actually a very tightly integrated GPU QPU system. So it enables us to have a very low latency link between a GPU and the actual quantum control hardware of a QPU. So we're starting to get the first results out of this at the Israel Quantum Computing Center. This is a machine deployed by Quantum Machines. It's connected to a Rigetti superconducting qubit chip, and there's several folks who are putting out some really fantastic work on it, leveraging the GPU to do some real-time calibration and optimal control type tasks. So we're very excited about that.
And if I may answer my own question, a year ago here at Q2B, we talked about an experiment that was done at Harvard with substantial support from QuEra, demonstrating 48 logical qubits. And one of the things we did this year is publish a paper on what's called algorithmic quantum error correction. I'll give you all the details in my talk tomorrow. But basically, we're showing about a 30x speed up in the time it takes to execute a circuit through much more efficient error correction. Now, Mike, I wanted to ask you, the papers, including the New York Times and Bloomberg and so on, were sort of very ecstatic about the Google milestone, and congratulations to you and the PR team. But the question is...
And the scientific team, but yes.
Congratulations to the scientific team and the PR team. But the question is this inside baseball? I mean, meaning, should a Fortune 500 company just drop everything, stop all their AI projects, and rush into quantum based on what you did? Or is this just another, perhaps important milestone towards where we all want to be?
No, I mean, it's certainly an important milestone. It's not like we're immediately going to be, running really, really large-scale algorithms using the chip we have now. I mean, we have 100 qubits, right? And you need, for an error-corrected system, probably at least tens of thousands, if not hundreds of thousands of qubits to actually get these these systems that will actually provide commercial benefit, or at least the long-term commercial benefit that we expect. So we're very far off from that. But on the other side of the coin, I would say that in order to actually reach those systems, the whole point of what we showed is that we have a system that can fundamentally scale. Like, as we make our logical qubits bigger, our encoded qubits, we do more error correction, the error rate goes actually down. So in principle, if you could take that 100-qubit system and copy and paste it, about 1,000 times, you would have a system that would be able to solve commercial problems. Of course, copying and pasting is a lot easier for me to say than to actually do. Like, there's a lot of actual really serious engineering challenges in scaling up. So that's, I would say we're kind of accelerating quickly, but certainly we're not at the point where you should not, as a Fortune 500 company, divest from your AI and follow us. You should do something, you should wait a little bit.
And let me ask a similar question to Jeremy. So first, again, congratulations both on the scientific team and also the graphics team. You guys had a really beautiful ebook and audiobook related to that. But your roadmap says 2030, I think. So what should companies do? Just keep listening, or is there anything that they should be doing between now and then?
Yeah, that's a great question. I'll take the praise for the PR team. Yeah, our roadmap's very colorful, so even if you're not that interested in what we're doing, just go and have a look at it for the colors. It'll brighten your day. So yeah, I mean, in the roadmap, what we show is that, and Mike just said that there was this overhead of about 10,000, 100,000 qubits to reach a machine which was useful. And what Alice and Bob does is we harness the fact that we have a noise bias in the qubits to make our devices extremely hardware efficient. And so we think that for a 100 logical qubit device, it's going to take us about 2,000 physical qubits. So compared to the numbers that Mike just gave, it's about a factor of 5 or 50 below. It depends on the range you consider. And so with a smaller number of qubits, physical qubits, you're going to reach systems which are already looking like systems which you might be able to run useful applications on. And the deployment time for these systems, if you go into a HPC center or things like this, it's on the order of years. And so 2030 is not that far away, right? When you think about it like that. So I would say you need to be kept up to date, and I would definitely start thinking about how I'm going to start apprehending using quantum technologies and perhaps trying to run some sort of subroutines of the algorithms that I'm interested in on systems which are coming out with error-corrected logical qubits within the next years.
Przemyslaw, I wanted to ask you, you mentioned that you take the long-term view at Amazon. Is there something that companies should be paying attention for error correction today, given what you said?
So I think last year was very exciting from both experimental perspective, but also from theory perspective. And we've heard about that in the IBM and Google talk, lots of progress on efficient quantum low density parity check codes, how to realize them in experiments. I think that's definitely something which people should pay attention to. Lots of exciting work on the decoding side. I think that's a really critical part of the full stack to really have the real-time decoders. So I think the field and also we internally are making like lots of effort to improve that. I would like to also like highlight our work on really considering end-to-end resource estimates. Like here it was mentioned, some estimates probably for the material science type of problems, but we really estimated with collaborators how much resources you need to really encode your problem, measure, include all the primitives, classical and quantum, in all those interesting and relevant problems the field is considering. And we have a really long but insightful survey about that.
Jin-Sung, you have a unique perspective because NVIDIA works with so many hardware vendors. What do you see as the timeline for useful quantum error correction?
Well, I think we're starting to see some very early indications that this is a real thing. So just looking at the past year, there's been several very, very impressive demonstrations of logical qubits, and I think that's a good sign. You know, in the past couple of years, we've seen qubit numbers go up and up and up. But for the first time, I think we're starting to see qubit numbers go down because we're starting to look at logical qubits instead of physical qubits. And this, in general, I think is a good thing. So, you know, generally, I think it's accepted that most of the useful quantum advantage use cases are going to be in the regime of fault-tolerant quantum computing. So this is really the first steps into the regime of getting to useful quantum computing.
When we look at the progression of the industry, I think the industry went from can someone actually build a quantum computer that does something to can someone correct errors in quantum computing? And now we've seen, for instance, from Google, we can increase the code distance and reduce the errors and so on. What do you guys, let's sort of take it right to left, what do you guys see as the next frontier? What's the next big step in error correction towards reaching the ultimate goal?
Yeah, well, I really like that question, given that we published the roadmap last week. Yeah, I think, so first of all, I just think Alice and Bob really believed in error correction from day one. So this is something that we've been saying since we were founded in 2020. We said from day one that the only way to really reach the value which will be unleashed by quantum computing is to concentrate on fault tolerance. And it's something that we're working towards, have been working towards, are working towards since then. And we're currently developing a chip which is able to run quantum error correction experiments in the same way that, I mean, Google and I think AWS have done this year. So shout out to them. I think that's, you know, we should recognize the fact that they're really good results. I think the next stage, I guess there are two next stages for me. The first would be that, you know, having a memory experiment is a really nice proof of principle. It's very exciting from a physical perspective, but if you need to do a computation, you need to be able to connect the qubits. And so doing logical gates is a whole other kettle of fish. both from the physics perspective and from the engineering perspective, which is sort of the second point, is I think now the question which we need to answer is that we know the physics works. I think that was demonstrated this year. Now we have to confront the engineering problem. And the engineering problem just doesn't look that easy. Really doesn't. And you know, what are you going to do with, how are you going to fit all these qubits on a single chip? How are you going to wire the fridge? What's the energy consumption of the device going to be? You know, like, are you going to, you know, all these questions are things that we need to find pretty creative solutions for. And at Alice & Bob, we think that the easiest way of solving these problems is to reduce the qubit count from day one, which is the whole premise of hardware efficiency.
So engineering challenges primarily. In QuEra, we say that if engineering were easy, we'd have the PR team do it, right? But, Mike, what do you see as the next frontier for you?
Yeah, I would echo a lot of what he just said. I think that what we've seen in the past year is kind of proof that the science works, and that primarily it does kind of go from a science challenge, can we build it, to an engineering challenge, when will we build it? I want to kind of hit a more optimistic note with kind of a story, well, a small story, which is that about a year and a half ago, we had this other work where we showed this error correction, similar to experiment to the one that Hartmut presented, going from distance 3 to distance 5. And when we presented that, the error rate went down by about 4% when we went from distance 3 to distance 5, a tiny, tiny fraction. And when we first ran that experiment, it was not that. It was worse than that. And we had to work very hard. We calibrated the device. We learned things about it. And we were just pressing and pressing. And the error rates were going down very, very slowly. And the reason for that is, again, because we were at this kind of inflection point where we were right around where the threshold was. And when you make small changes right around that point, you don't get too much gain. This year, the story was basically totally different. You know, the first time we ran it, it kind of worked. And then as we made improvements, it improved extremely rapidly. And the reason is basically that when you're below the threshold, or when your system is kind of working, error correction gives you this basically exponential leverage to make things better and better, faster and faster. So something I like to say about the Willow device, which is this new device we have relative to Sycamore, is that the error rates are roughly twice as good, but the encoded error rates are about 20 times as good. And that's because every small physical advancement you make when your devices get good enough are exponentially amplified with error correction. So, you know, it might seem like we're kind of still far away, but things are accelerating quite quickly at this point. And so, yes, it's an engineering challenge, but I think that we're going to get some leverage out of continuing to improve our systems, and those improvements are going to be amplified exponentially. Yeah.
In Jin-Sung, I would guess that maybe one of the things you care about is hardware, or, you know, accelerated decoding, actually.
I was exactly going to go there. So one of the big challenges that we're looking at today is how do we tightly couple HPC resources and accelerated resources next to quantum processors. And one of the biggest use cases that we see here is doing decoding. So this is a very difficult HPC problem, and it scales. So once we're at the scale where we want to start attacking, you know, interesting scientific problems with a quantum computer in the regime where we won't be able to attack these with classical computers, this is actually a very difficult decoding problem. So some conservative estimates take us to of the order of petascale compute next to a quantum processor just for the decoding. So what we're thinking about is how do we best leverage GPUs and things like this, accelerated computing next to a quantum processor, to actually be able to do the decoding at interesting scales. So it'd be, the ultimate irony would be if the quantum computing hardware developed to the point where we could actually do quantum error correction, but the classical computing couldn't keep up with it. So this is why we're invoking accelerated computing and GPUs for doing decoding.
And just before we go to Przemek on this, I'm curious, there are other companies who are developing ASICs for doing the decoding. So why use a GPU?
So there's a couple of very good reasons to use a GPU over something more like an ASIC or you know, an FPGA. And one of these things is the programmability of using a GPU. So there's a very mature infrastructure of leveraging single, multiple GPUs and supercomputing scale GPUs all within the same programming framework, as opposed to doing something custom with an ASIC and building a larger ASIC for each iteration of quantum processor. And there's also an existing infrastructure that we can tap into for doing this already today.
And Przemek, what do you see as the next frontier in error correction?
Yeah, so here, like just lots of great points were made. So I will just try to maybe mention two things which I think weren't mentioned. So one thing is like starting to think in terms of really logical operations and going beyond memory. It was mentioned, but like lattice surgeries, the thing we think, at least for solid state platforms, is the way to do it. And there is lots of things to do on this front. As we have larger devices doing 2-qubit gates, T-state preparation, or some other flavors of preparing states, non-Clifford gates. I think that will be the near-term type of effort in the field, and doing that on like multiple qubits. And longer term, I would like to just highlight that we know how to more or less scale it up to some level. We know maybe we can brute force it to 1,000 or 10,000 of qubits. But I think in some sense, it's not only engineering effort beyond that. We really need to invent new ways of controlling qubits, but maybe also take more holistic approach and modify our underlying architecture so that controlling them is easier. Control is very expensive, and I feel like in my dream, we would have ideal qubits and we could just control them, with few signals, multiple qubits, and I think that's something which the field, at least in superconducting qubits, needs to address. And that's why I think, like, at least at our place, we have a really interdisciplinary team. We are thinking on different timescales and thinking medium and long term. And I am excited to also collaborating. We are excited to collaborate with academia and industry.
At QuEra, we're running circuits with some logical qubits in the lab. And I think for us, we see a couple of challenges. One is really to run universal circuits, right? With logical operations, right? So how do we get there? The other, it seems to be that at least in our architecture, there's a ton of software that needs to be written between the, well, here's what I want to do and here's how it actually gets done in the hardware. In neutral atoms, there's a lot of degrees of freedom. You could move qubits around. How do you do it efficiently? How do you minimize the movements? How do you parallelize the circuit and so on? So, and the third thing, as Jin-Sung mentioned, is probably hardware efficient decoding. How can we get the maximum bang for the buck there? I was speaking with Scott Aronson on the break, and one of the things he told me is that he was surprised that at this point in our sort of professional lives, there's no single modality that's really broken out as the absolute obvious best way to reach quantum error correction. So, Jeremy, why don't I start with you? So if cat qubits, if tomorrow morning the science team comes and says, it's just not going to work. We can't, cat qubits are dead. No, Theo, your CEO, last year in this panel said no cats were harmed in the production of this panel, right? But let's assume cat qubits don't work. What are you going to do next? I mean, not personally. What's the next best modality for you, in your opinion? And of course, I'll go down the line with that question, so you have time to think about it.
So thanks for not giving me any time to think about it. Yeah, I think so. I mean, the problem quantum computing is a difficult problem, right? And it doesn't really matter which path you take. There are always going to be difficult problems you have to solve. And I think this has been demonstrated. I'll take an example from the AWS paper, which came out recently, where the frequency targeting of that paper to run the repetition code experiment is very impressive. The frequency targeting is really on point. And I'm assuming that this was a very difficult problem to solve because frequency targeting is known to be a difficult problem in superconducting circuits. And at some point, someone had to choose and say, we're going to solve that problem. And so I think it's difficult to say, if cat qubits won't work, what's to say that a different platform is going to work better? At the point at which we say cat qubits aren't going to work, why is it that we think that something else is going to be better? So I would say that at Alice and Bob, we're just fully committed to the technology. We know there are going to be steps which are difficult. I mean, in a sense, I could use the argument that we haven't, there hasn't been like a consolidation in a single technology because all of the technologies are hitting roadblocks at different times and solving them concurrently, right? So I think you have to be a little bit, yeah, I think the focus is really important. Yeah, we're choosing, as of last week, we've sort of chosen publicly a direction which we're going to take. We're committed to it. There are hurdles along the way, and we'll just have to climb over those hurdles when we get to them.
And are there specific problems for cat qubits that you perhaps don't see in other modalities?
Yeah, so I think one of the things which is more difficult with cat qubits than perhaps other superconducting circuits is just the level of the maturity of the technology with respect to the community. So platforms based on transmons, for example, they're leveraging a huge community base which work on transmons and a lot of historical research on this topic. And so although we're convinced that our system is probably the simplest in the long run at large scales, you know, developing all this know-how on a much smaller community is hard. And so I think this is a typical difficulty when you choose a more specific hardware platform. And so we're really happy to see that there are other companies like AWS who are following suit. We really pioneered the cat qubit, and AWS thinks it's also a good idea. And having the academic community around us who work on the system, that makes things a lot easier.
And Mike, if superconducting are not so super anymore, what do you do next?
I feel like you didn't really answer the question. I'd like to hear it. All right. This is just me personally, but I choose atoms. I think that I'm very excited about atoms. I obviously think superconductors are sort of the most exciting technology for me. But I like the fact that they have parallelizability. I like the fact that there's sort of an intrinsic multiplexing that you get by shining a laser at multiple atoms and having them sort of interact in the same way. I worry about the number of microwave signals we have in superconducting qubits. At the same time, I really like the speed of superconducting qubits. Like, that's a big deal. When you actually look at the timescales for running useful quantum algorithms, it's daunting. And so for architectures that are faster, like superconducting qubits, they will have an intrinsic advantage. Now, there are ways of overcoming that. One thing that you mentioned, for example, with this algorithmic fault tolerance, was that you can speed up the logical computations, but that still doesn't make up the entire gap. And so that is something that I worry about long term with atoms. Yeah.
And Jin-Sung, maybe you have the most difficult time answering. Do you have a favorite son?
So we are very intentionally qubit agnostic. So you'll see we've integrated with every modality of qubit that exists today. We have a new integration with QuEra. We've just integrated into Amazon Bracket. So from our perspective, we extremely strategically have strived to be a platform company. So we really intend to be the tide that lifts all boats within this space. So, I mean, if we look at the past history of quantum computing, there's been many, many lead changes, say. Every couple of years, there's been some new breakthrough in some new qubit architecture. So for us, it's very difficult to say, and to make a determination of a winner today that won't be wrong in the next couple of years. After
Przemek answers the question, I would love to give an opportunity to the audience. So start thinking about what you want to ask the panel. But Przemek, please.
Yeah, so like AWS was founded in AWS CQC, so Center for Quantum Computing was founded in 2019, and we really did our due diligence, given that the field was reasonably already set up, like what are the advantages, disadvantages of different platforms. And we are pretty excited about superconducting qubits for like one reason which was mentioned is the fact that, remind me, Mike, what did you say?
Speed.
Speed, yes.
Yeah.
Speed is, my background is partially in neutral Rydberg atoms, so I am also like, I am really excited about the progress. But the speed is really important for us. But another thing is microfabrication. So like how the fact that you can bring so many lessons from conventional transistor silicon-based fabrication. And another one is scalability. We think that you can really scale it up. It's not like some other maybe architectures where it might be very challenging. And our approach is to really focus on fault tolerance, but simultaneously not really exploit one single direction, one type of gate, one type of qubit, but really explore, but not too much. You cannot explore everything. So there is always finite resources in every organization. So we try to spend quite some time on deciding our priorities and really split this effort into those different buckets. And one is really like thinking about this hardware efficient quantum error correction, but another one is scalability. And hopefully you can, replace components whenever you find the better one down the road into the whole stack infrastructure without too many changes. So that's basically our approach.
I had the CEO of one of the quantum companies on my podcast, and he was extolling the virtues of his modality. I forget if it was NV centers or silicon qubits. And I asked him, well, okay, so if it's so great, why isn't everyone doing it? And basically came down to, it takes 20 years to build experience in that. So if you are a fantastic cello player, that doesn't mean you can switch to oboe tomorrow morning. It just takes a lot of practice in the particular modality that you're using. So why don't we take a question from the audience or two, if that's okay? Who's got the first one?
Right down the middle.
Please. Yeah.
My question builds on your last question to the panel, which is, so if we had coalesced on one modality, whether or not it's the best one or not, can you assess whether we would be much further ahead? Would the industry have structured itself around specializing in companies that then can only focus on compilers, other only focus on the cooling problem, other focus on, I don't know what, manufacturability, et cetera? Would we have gained a decade, or would we be pretty much in the same place because the bottlenecks are the bottlenecks? Thanks.
Yeah, that's a great question. Yeah, I think it's difficult. One of the big topics and I think it's a bit wider than just quantum, but like in deep tech fields, is how do you transition from what I would say an academic group on steroids to an actual business. And so these are things which you have to tackle, which people don't really talk about because we're focused on the tech. And I think some of the big results, there are big results coming out of academic groups in partnership with companies or in companies which are organized like an academic group, and that is inherently not scalable. When you build a big machine, you have to reorganize the structure of the organization. And if we had brought all those people in at whatever timeline you're imagining, we would have had to confront that organizational issue, and it takes a lot longer than you expect to confront it. I would say it's on par with some difficult tech problems, and so I'm not sure there would be. I'm not sure. I would answer that it's hypothetical, right? But that's definitely a problem that we would have faced. I'm not sure we would have gained that much time.
So I think the answer is no, we would not be better off if we had coalesced along one specific architecture. I think there's a couple of reasons for that. So one, just the general reason that competition breeds innovation. And what we've seen within the field is that many times techniques are developed in one field that are borrowed by another field. So to give one very concrete example of this, many of kind of the pulse and the control techniques used for developing 2 qubit gates in superconducting qubits, say, many of those techniques were actually borrowed from the NMR community, which was developed back in the 70s and 80s. So if we had coalesced along one of those lines, then some of these techniques would not have been able to transfer to the other architecture.
Please.
Yeah, I think I partially agree. I would say that I would put the reasonably large probability that we would be a few years ahead today, but there would be very high risk that we would be many years behind in 10, 20 years. I think you could optimize in this local optimum without new ideas or without really exploring other directions and platforms. And there are like lots of transferable ideas on the quantum codes ideas and so on. So I think on the same on the hardware. So I think like we should not try to optimize too early, not exploit too early.
And I'll just say that having multiple qubit modalities is a form of error correction on getting the whole thing done. Like, it could be the case, like none of these technologies has really explored the error rates very carefully that you need to explore in order to be sure that this is all going to work at the 10 to the minus 15 or 10 to the minus 12 scale. So, it would sure be not so great if we all invested in XYZ technology and then we were like, oh, there's a fundamental physics reason why this is going to be a problem later down the road. And we've seen that those types of things happen before. Like, it's not an unprecedented issue. So, yeah, I would say that it's a form of error correction.
And I want to ask Jeremy, perhaps the last question on this panel. On the left side of the stage, we see these giant companies, Amazon, NVIDIA, Google, that probably have more revenue than most countries have in their GDP. But then you have smaller companies like QuEra or Alice and Bob that perhaps cannot afford to do everything ourselves. What kind of collaborations, what kind of partnerships are you looking for to help you accelerate the goal?
Yeah, I think you're right. As a smaller company, you have to remain even more focused and really choose the battles in which you're the expert. And leaning in on that expertise actually simplifies a lot of the problems you're not an expert on in the long run. So that's already a big advantage of the focus. Now, I mean, I can cite two problems on which Alice and Bob is not an expert in general. It's the control electronics for superconducting qubits. This is, I mean, we know how to use them and do stuff like this, but we're not builders of quantum control electronics. And for example, decoding is also something that we have knowledge on, but not necessarily neither like the real computing expertise nor the hardware infrastructure to do these things with. And so these are the type of topics that we're going to look for partnerships with. And for the decoding problem, for example, we've been working a little bit with Riverlane on this issue. So yeah, I think you have to recognize being a small company is being able to look at yourself in the mirror, say, what am I actually good at? What should I really emphasize on? And we know that we have strengths. We have strengths in qubit design. I think we've demonstrated that we're really good at designing new types of cat qubits, really leading the race there. And so we should lean in on those strengths and look for people who are really good at FPGA design for control electronics.
How are we doing on time? We're done. Okay, very good. Well, thank you very much. Please, I think many of us will stick around for the entire show, so please catch us during the breaks or at the exhibit hall.